Okay, so let's talk about what is a solution. Who in here has not heard of the word solution? Anyone? Okay. A solution is two or more substances that could be a solid, liquid, or gas. Most of the time we think of solutions as liquids, but it could be a gas or a solid. And they have to be homogeneous. In other words, you can't tell them apart. For example, air in this room is a solution. We've got two or more substances and they're homogeneous. You cannot tell them apart by looking at them. Sugar and water. Sugar and coffee. Gold and rain. Solution. Gold and copper. You can't tell them apart. So solution could be solid, liquid, gas. We mainly focus on the liquid part. And it has to be homogeneous. For example, oil and water. It's not a solution because they're not homogeneous. Heterogeneous. Okay. There are always two parts to solutions. There's the solvent and the solute. You can have more than one solute. So for example, going back to gas, the solvent is nitrogen gas, so that's the most gas. Solutes will be oxygen, carbon dioxide, and then carbon monoxide, solute. Sugar and water. Water is a solvent, sugar is a solute. Gold ring. Depends on how much you pay for it. How much is the solvent, which is the copper. Whatever's the most is the solvent. You have to have at least one solute and only one solvent, no exception. You can have multiple solvents and only one solvent. So we're going to focus the rest of Unit 5 on liquid solutions. So let's take salt and water. Let's look at it microscopically. As you all know, sodium chloride is a formula for salt. It's an ionic solid, meaning that's made up of ions opposed to neutral elements. Sodium chloride is positive one, and chloride and negative. That's how they are solid. So that'll be our solute. And our solvent is going to be water. And if you think back probably a month ago or so, we found out that water is very polar and it's got a negative part to it and two positive parts to it. And those are partially positive, partially negative. That's what that squiggly thing is all about. You get into partial differential equation in calculus, that's considered the calculus. Partial signs in math. Okay, so we have a polar solvent and a polar solute. Now, there's an expression that's commonly used. It's like dissolved like. So, in this case, polar dissolves polar. So we've got polar solutes, polar solvent. So do you think salt will dissolve in water? You know, because you've experienced it. And secondly, it's like dissolved what? Polar like, polar like. What do you think about oil in water? Okay. Now think about what I just said, like dissolved water. So it's oil like water. They don't dissolve. Just by observing that, you know that oil is very much unlike polar water. Oil is correct. Yes, unpolar. Now think about your car. All right, I just found a new G in my car. It's Sac City's parking lot. Nice. Full size picture. But it's just like the same car. Anyway, so driving your vehicle, you just washed it, it's nice and clean, and your only way out is on an oily road. Recently oiled. What happens to your car? Well, it slides, but think of splattering that new oil on you. So you get home, you just wash it, you're all upset. How can I get rid of this oil? How would you get rid of the oil? How would you make it dissolve some liquid? You take your garden hose, spray it. Why would the garden hose not work? Like dissolves light. The oil is non-polar, water is polar, so it has no effect. So what's another way to get rid of it? There's 2 ways. Take your 408, right? Or go inside and get some vegetable oil, which is non-polar. Rub it, and get rid of that black oil on your car. Then get rid of the vegetable oil, which is easier to get rid of. Okay. So I'm going to talk about something called we can talk about soap. Soap is called an emulsifier. We're going to talk about that in terms of solution. Okay, so let's look at microscopically what salt and water does. Okay, so we've got a crystal. Sodium ions and chloride ions. And we're surrounding that with water. So we've got a charged particle here. Charged particle. Now, who I charge trap or withheld? Trapped. That means these hydrogens are going to trap the negative chloride. This negative oxygen is going to trap that sodium. They're opposite charges. So in the crystal, salt crystal, these are going to be polar out. That's polar salt. Okay. Which add on that temperature is a measurement of kinetic energy in a molecule. It's a metric used to measure the kinetic energy or movement molecule. So these guys are moving big time. So that's continually bumping up against the salt. So what do you know when you have cold coffee or hot coffee? Which dissolves sugar better? Hot. Now think about what's going on temperature-wise. Hot temperature means the water is vibrating more. So statistically, the chances of hitting that are higher. Because it's moving more. Now, if we brought this down to absolute zero, minus 273 centigrade, that's not moving at all. So minus 273 or zero Kelvin, which is absolute temperature. You cannot dissolve that salt. The temperature will affect how much the solubility happens. Because of increasing the chance that things vibrating and moving around, that will hit that surface of that salt crystal and pull it out. Okay. Let's now, so this is time 0. Let's go to time some seconds later, minutes later, doesn't matter. What's going to happen now is that sodium is going to be surrounded by water. Hold it out of the crystal. Chloride is also been pulled out and surrounded by water. Only the hydrogen trapped in chloride rather than the oxygen. Now this is pictured in 2 dimensions, but it's really 3. So it's a sphere, not a plate. Okay, and that structure is called a hydration sphere. So think of your dissolved salt and water as a whole bunch of sodiums in there surrounded by water, a bunch of chlorides surrounded by water. So you have all these hydration spheres, keeping them from going back to the crystal. And that will make sense on why something dissolves. Okay, so let's now take another example. What is silicon dioxide? What do you think that is? Oh, sand or glass. Okay, so let's put sand in this water, okay? Now, what happens to the sand? Does the sand dissolve? Does the glass dissolve? No. This is polar, that's polar. Polar dissolves. Polar. Why does it dissolve? So now it's the water. Okay, so we have the same situation. The same situation is this. We have polar solid, polar solvent. Polar solid, solute is silicon dioxide, polar solvent. There must be something going on here. Why does one dissolve and one doesn't? Okay, So we are going to, you talked about video games, right? I'm going to talk about two forces, familiar? And they are going to battle each other in this scenario. One force keeps the crystal together, the other force pulls it apart. And whoever wins is what happens to the solvent and solute. Okay, if one force that keeps the crystal together is stronger than the other one, it'll stay together. If the one pulling it apart is stronger, it pull it apart. So those two forces are, one is solvating. Solvating force pulls the crystal apart. The other one is a crystal lattice force that keeps it together. So we have the crystal lattice force battling the solvating force. Which is stronger here? Solvating or crystal lattice force? Huh? Remember, crystal lattice keeps it together. Solvating pulls it apart. So with the salt in the water, right. Okay, the solvating force is stronger than the crystal lattice force. So in this situation, the solvating force, I'm going to abbreviate because it's too long to write, is greater than crystal lattice force because it dissolves. Down here, the crystal lattice force is stronger than the solvating force because it doesn't dissolve. So you always got a battle of these two forces going on. Okay. Now there's very, yeah. That's a good question. Which determines which is which? There are two things. One is the nature of this. And how stable it is in this environment. For lots of reasons. And the other one is, which one of these you think is solving for? Solving, remember? Vibration, temperature. Temperature is a measure of movement, anything to the molecule. If they freeze, then the solving force becomes stronger. You can act more like a solvent. If we cool it down, it's like they make a octane. You start with hot sugar water and let it cool down and crystal down. The temperature of the water goes down, solving force becomes less, and the lattice and so on. Okay. So your point is well taken away. Also the structure of the crystal itself. How stable is it in the solvent environment? Okay, so that's what's going on here. Now, I want you to understand this concept of how does a solid dissolve in a solvent? How does a solid, with this big water table, how does water dissolve sugar? The sugar is running on that solid, it's very cold, because we know that one. Dissolve. Dissolve in what? Dissolve in a polar solvent, hence the solvent has to be polar, otherwise it wouldn't dissolve. So what happens with sugar? If you took my OChem class for nursing, they knew these structures backwards and forwards. This is what glucose looks like. See, what does the predominant thing that sticks out from that? Huh? Oh, wait, hydroxyl group. Yeah. Carbohydrates have tons of these. Tons. This is glucose, sucrose, table sugar. You've got two of these together. Also, the two of these together. Bottom line is the OH. What does water have on it? Does it have an OH on it? Yeah. I get 2 and 1. So OH, OH, like to like. One of the reasons carbohydrates dissolve in water so much like more complicated. Basically, almost like hydroxyl groups, the OH groups, like water so much. So you're going to have the same setup. You're going to have the water hydration sphere surrounding that glucose. So that oxygen is going to be attracted to that hydrogen on the hydroxyl groups on sucrose. And that's what the hydration sphere can look like for glucose and water. And the crystallized forms for glucose, where the water solid. Always keep those two lines, solving line. Okay. I want you to be able to explain that. For Unit 5 test. Okay. All right. We're going to talk about one more thing here. Okay, so you all know that oil and water don't mix. Based on our previous discussion, why?
One's polar, one's not.
One's polar, one not polar. Okay. I made some meatballs last night. And I used a really greasy. I put it in water, my pan will be clean. Why? Yeah, water is very oil. How can I clean my pan? How much do you wash dishes? You wash dishes with water and oil? Water and soap. Why does soap work? It's like getting rid of aphids. Soapy water, right? Okay, so we need something that's got something that's polar in it and something that's non-polar. That's called soap. Because soap, I want you to think of like glue. People glue an oil molecule to a water molecule. Why do you think that? Remember, like, well,
Is it because they, so, it's like, both,
that's right. So the polar can bind to the water, non-polar can bind to the water. Six, and this is that. As far as our situation here, if we wanted, we're making a vinaigrette tonight. Okay, oil and dilute acetic acid in water. It's called a vinaigrette. Okay, you can shake it up all you want and nothing happens. It immediately separates again. Who makes vinaigrettes at home? Anyone? How do you make it? Oil and what?
oh,
Yeah. How do you make it? No one here makes their own vinaigrette. Wait, how do you make a vinaigrette? Good point. Oh, on earth. It's like, okay, this is the way I make vinaigrette. I take vinegar and oil. I mean, that's something. Not so. Okay, that's something in there that will bind to the oil and bind to the water. So that when I shake it, it stays. So I added mustard. I added Parmesan cheese. What about this is the two main ones. Salt and basically that's it. You want to do that? So it's most effective one to use. Parmesan cheese. Shake it up. And they have a emulsifier that will heat. Yeah. Just like so you want. Now there's a fancy word for soap. Called a surfactant. Also an emulsifier. And the soap is both a surfactant and an emulsifier. What? Why not? We're always talking. That means the water vapor in the glass is attracted to the plastic on my bottle. It forms a little blob of water. What it did is I sprayed on the bottom. It brought the plastic firmly to the water. And what's out? They actually more polar. So the water was more attractive. But that was more attractive. The water droplets became very weak. So when the light went through it, the light enters water, refracted again. So the smaller the droplet of water, the less it's bent. When we're even though it's bent off. Most people think put that in the bottom the spurt. My dance like Very next, you windshield on your car. All those things of fog. Glass, plastic, more hydro, water. Okay, and in biological systems, these emulsifiers are extremely important. Because your body, the big sack of water, most can get out of water. That's why you should not put living things in a microwave. Because they're going to get out of water. And microwave will speed up water molecules. And you can lift the air, well, wash your hands. Stop wood. Doesn't put What is an effect copy? You're gonna live. Okay, so how do you define keep everything straight? For example, your stomach is filled with what bad liquid? Stomach gas, hydrochloric acid. Yeah, doesn't hurt you. That's the one place your mind where it's hydrochloric acid. There and at the top of the small intestine.
Happens.
Hydrochloric acid is extremely polar. What did your stomach have in it? That contains- There's another problem in the body is how is one part of the cell have reactions, have a water, and another part of the same cell has got separate reactions. How do you define keep those apart? Biology. How do your body do that? Huh? How does your body, like a cell, keep one reaction separate from another? A membrane, exactly. Cellular membrane. Membranes, guess what? Are non-polar. And the non-polar membrane keeps one water reaction separated from another water. With the shape, and they're all fragmented. And they're with the membrane out. Exactly. So by bottom line is the phospho liquid is non-polar. Keeps water stuff out. There's little gates in there that determine what's going in and out. Gates can turn on, turn off by using that activity. Basically, it's non-polar walls put up in your body called cellular membranes. It keeps one water reaction from interacting with another water. There's one that surrounds the nucleus. There's mitochondria membranes, or your combustion design in the body. Catalyzed nucleus. So this concept of the multiplier spectrum biologically is extremely important. We would not be, I would not be standing up here talking to you if my multiplier was not picked up. A lot of diseases do that. For example, sickle cell anemia. Who's heard of sickle cell anemia? What is it?
Cells kind of sickle and you get stuck in arteries and veins, but it's like no, sorry, I was thinking that's how it also counteracts malaria, but yeah, you can get a lot of strokes from it. They kind of clump together.
The difference between a red blood cell, a normal one, right? It's like sickle cell anemia, like you're saying, is really pointy. Difference is one amino acid was changed 2,000 years ago from polar to non-polar. One amino acid. Anyway, because of the difference between the two, shape of the cell. And when they change, it can't carry as much oxygen. So it's a very painful disease. It tends to affect the joints because that's where the smallest capillaries are. They tend to build up in those areas. And the die from the almost homozygous version of it, or the heterozygous version, die or if the heparin one is extremely painful, but you would say that. But in the pure, it's biological engineering. And that's being done today. That's not science fiction. Okay, so this polar non-polar bit is really important. Biochemically, non-biochemically. It's just a really important concept to get across. Okay. Then you've got two forces interacting with one another, the crystal lattice force and the solvating force. And the solvating force is affected by temperature. Oh, I forgot to mention, there's one other thing that okay, so what affects solubility? Okay, I already mentioned the two forces. Crystal lattice force, solvating force, right? And so if we wanted to make something more soluble, what is the one thing we could do pretty easily? Temperature, yeah, exactly. So I want you to go back to your coffee. Put the sugar in there. Hot coffee dissolve more sugar than cold coffee. What else helps dissolve in coffee, the sugar in the coffee? Yeah, stirring, right? You don't stir it, doesn't dissolve. And what is that similar to? Yeah, it's similar to increasing the temperature because we're increasing the motion. Okay, so physical agitation will increase solubility. And there's one that's not so obvious. Going back to the coffee, which would dissolve better in your coffee? Granulated sugar or powdered sugar? Why would powdered sugar be dissolved? Smaller? Yeah, exactly.
And it's not as clumped together.
Let's put together. And remember, going back to our this is a surface phenomenon. It's only acts at the surface. If we increase the surface area by having a smaller version of that, surface area more. So increase the surface area, we increase the chances of colliding. Does that make sense? So those are the three things that affect solubility. Temperature, physical education, which are sort of the same, and then surface area. Okay, so that's the qualitative